Okay, so we should start. So it's a pleasure to have François Guéritaud, who will be speaking about boundary of the limit cone of Anosov groups. Unfortunately, due to visa issues, François could not come offline, come in person to ICTS Bangalore, but somehow we have been able to get him online. So François, please, over to you.
Thank you very much. It's great to see some of your faces, although you're very, very tiny on my screen.
Can you speak a bit louder? Your voice is not coming properly.
Okay, I will try to speak loud like this. Is that enough? And I can see most of you in the room, so if you have a question and you raise your hand, I should be able to notice that. You can also pass the mic around, and of course, please interrupt me anytime you feel like. So I'm going to report on ongoing work with my longtime collaborators, Jeff Danziger and Fanny Cassel. The topic is on the boundary of the limit cone. So there's going to be for roughly half of the talk, I will give broad strokes overviews of two areas. One, the random walks on Lie groups, and the other one, a specific topic in dynamics called ergodic optimization. And in roughly the second half of the talk, I will tell about our new insights at the intersection of these two subjects. So the general problem we are going to be interested in is you're given a finitely generated Zariski-dense discrete subgroup of a linear group, and you're interested in how fast the elements grow. So since you're a mathematician, you make this precise in terms of eigenvalues. You look at the logs of the eigenvalues sorted from largest to smallest. You call this the log spectrum of gamma, for example. It's also called the Lyapunov or the Jordan projection of your element. And you ask about how fast this vector grows in RD, right? For example, if you take powers of an element, you propagate linearly in a certain direction of RD. So one version of this question would be about the asymptotic statistics of the lambdas. And of course, we're talking about an infinite set. So to make sense of statistics, we need to say how we enumerate gamma. So one way to do this would be in terms of word length, or you could sort the elements of gamma by operator norm, since your group is discrete. In fact, you can do a lot of this without the discreteness assumption, but I'm going to focus on discrete for this overview. So sort them from shortest to longest by operator norm. Or maybe you know that the gap between the kth and k plus first eigenvalue tends to grow linearly, or tends to grow at all, and then you sort them according to that. So some sorting scheme, and you can ask about the asymptotics of the lambdas. And a very related version of this question is you could, instead of the lambdas, the eigenvalues, you could look at the so-called principal values. What are the principal values? Well, they are called mu. It's the length of the ith axis of the ellipsoid, the image ellipsoid of the unit ball. So if your gamma can be diagonalized in an orthonormal basis, in other words, if it's a symmetric matrix, then the lambdas are the same as the mu. Otherwise, there's a little nuance between the two. For example, this special example, a high power of a unipotent matrix has eigenvalues 1, so its lambda is 0. But the mu's, the distortion tends to grow. But you should think of this as kind of exceptional, and mostly the mu's should capture the same asymptotic behavior as the lambdas. The mu's, we're only introducing them because they are better behaved in their composition, so they are an important part of the proofs. So answer to this first question is, well, there's I'm really going to summarize a large body of results that people have obtained on this subject. The idea is that statistically, these elements, these vectors, they grow like sums of IID, random variables. If you're familiar, IID means independent, identically distributed. So the paradigmatic example is you flip a coin n times and you ask about the distribution of possible results, right? The probability of getting xn times heads out of n flips is proportional to this binomial coefficient, and we can estimate how those grow, right? As n goes to infinity for x fixed, those grows like powers of a certain function of x. So it concentrates at x equals a half, and there's a precise profile that's this function. Now, essentially the eigenvalues should grow as if you are just flipping a coin, except instead of just being heads or tails, it's, you know, maybe the first eigenvalue grows or the other eigenvalue grows. And you sum these, and that gives the type of distribution that you expect. So one thing that you expect is the law of large numbers, which says that things concentrate around a typical behavior. That's the max of this function here. So there's a ray here, close to which most eigenvalues lie, or most log spectra will lie. Of course, what this ray is will depend on your enumeration scheme, right? Maybe you enumerate the lambdas from according to growing first eigenvalue, and then the ray will be somewhere down here, or you enumerate them according to the increasing second eigenvalue, and then the ray will be somewhere here. And somewhere there's a ray, and the eigenvalues, they really distribute in some convex cone. And near the ray, you can focus on the behavior at scale root n for length n elements, and there's a central limit theorem. So there's a sort of Gaussian way that things distribute near the ray. There are also large deviation results, which tell you how fast, well, yeah, how fast the growth in a direction different from the ray is. There's still an exponentially large number of elements near any given ray in the cone, but the rate is largest for the central ray. You can ask for these other rates. So those are large deviation results. So again, law of large numbers, central limit theorem, large deviations. There's more. There's the iterated log law. All of these have analogs. You can convert the proofs for the point flipping problem to proofs about the distributions of eigenvalues. And the law of large numbers is about the maximum of this Gaussian. The central limit theorem is about the width of the peak, and large deviations is about what happens here. Now, what we would like to ask today, question number 2, will be what happens exactly here so beyond large deviations at the very extreme type of behavior of log spectra. So one notation I'm going to use is big lambda gamma. That's just the cone generated by the lambdas to take the closure. And that's a convex cone with non-empty interior in the Zariski dense situation. We're going to use this, and here are the names of some of the people who proved the results 1, 2, 3, and so on. I can recommend the book by Yves Benoit and Jean-François Quin that summarizes a lot of this and is written in a nice style. Okay, so question number 2 is how fast do these eigenspectra, these projectivized log spectra approach the boundary of the limit cone? Now here, importantly, it becomes important whether we deal with eigenvalues or principal values. The reason is that principal values are altered when you conjugate your group, right? You conjugate your whole group by a matrix M. That's going to mess up your principal values, your axis of ellipsoids. by a constant depending on m. So all you can say about the mu's is that they are in some neighborhood, some uniform neighborhood of the limit cone. But if you're interested in the behavior at scale, in a sense, less than 1, distances little of 1 to the boundary of the cone, then you should, it makes no sense to ask this in terms of the principal values mu. You should really be talking about the actual spectrum. Notice I haven't yet proved that there are points at distance much smaller than 1. Right? For all we know, things could approach the boundary of the limit cone in a sort of parabolic way. But that won't turn out to be the case. There are, in fact, points close to the limit cone. So in the same sort of large-scale overview, I'd like to answer question number 2 in the following way. You should forget about coin flips and identically distributed variables. It still looks like sums, but a different kind of sum. It's the sum called ergodic sums, specifically the topic of ergodic optimization in dynamical systems. So I'm going to, the next 15 minutes is going to be a little digression into the subject of ergodic optimization that people are maybe not so familiar with. So what you're given is a dynamical system on a set X, a space X. T is the dynamical system, and you have a scalar function f on X that you're interested in. It's scalar, or maybe it's valued in RD. And the question you ask is, which T orbits maximize what I'm writing in this way with angle brackets, fxt. What is this? It's the limit, if it exists, I'm not going to worry about this, the limit of averages of the first n iterates, of f of the first n iterates, right? So if d equals 1, you try to maximize this number, and if d is positive, then you try to maximize this vector in a certain direction, eta. And you call this line of questioning ergodic optimization. So you're looking for the best possible orbits, so to speak. And here's a very important example. X is the circle. T, the dynamical system, is just the angle doubling. And that's, you should think of this as a hyperbolic system. I don't know how hyperbolic it looks to you, but in dynamics, it's called hyperbolic in the sense that it has very little memory. If you have 2 points that are very close, they diverge at rate 2 to the n from each other. So soon enough, you know nothing about the relative positions of the 2 points. That's sort of the hyperbolicness of the behavior. And the map that we are going to study is the map valued in R2. That's just the ordinary parametrization of the circle. So don't look at the theorem. Let's study what happens to f of 0, for example. If you start at the point 0 and you double angle, you stay at 0, and you stay at 0 forever. So the average is 0. And the average of f is f of 0. It's this point. If you take a random number, a random point on the circle, you double, it's going to usually equidistribute and on the circle. So the average will very soon be very close to 0. So most points have an average fxt that's 0. However, there are some special points. For example, focus on the point 1/3 here. If you double, it goes to 2/3. If you double that, it goes to 4/3, which is 1/3. And it keeps flipping between these two. So on average, it's this point at -1/3. Right? On the horizontal axis at -1/2 cos of 2 pi over 3. So 1/3 is kind of special. In fact, every rational point will cycle back to its starting point. So its average will tend to be some number that has no reason to be 0. For example, let's take 1/7 doubles to 2/7, doubles to 4/7, doubles to 8/7, which is here again. So we have the vertices of this heptagon. And we cycle between those 3 vertices. So the average is over here. And you can prove, it's not trivial at all, but you can prove that this is the highest point you'll ever get, the highest average. and 1/3 was the leftmost. Of course, 0 was the rightmost. Okay, what about other rational numbers? What about 1/5? Doubles to 2/5, doubles to 4/5, doubles to 8/5, which is 3/5, which is here. So you get 4 vertices of this pentagon. And on average, the 4 vertices, they give you a point somewhere here. So not the origin, but somewhere inside the convex hull of the previous ones. So there are some rationals that are special because they give you extremal behavior, and some that aren't. So this was conjectured for a while and was proved by Thierry Busch. His theorem is that if you take the convex hull of all possible averages, fxt, you get this region P, which is, well, it's convex, and its extremal points are exactly the images of the orbits of the rational points whose base 2 expansion is a special kind of word called a Sturmian word. What is a Sturmian word? It's a sort of perfectly equidistributed or perfectly balanced 0-1 word. It's what your computer does when it draws a straight line with pixels. It has to go left, left, right, right, up, right, right, up, right, right, maybe a third time, right, up, and so on. So you take this straight line, you look at in what order it intersects vertical and horizontal grid lines, and that gives you a word over 2 symbols. And that's the kind of period, that's the kind of rational that we're interested in. So for example, 1/5, which develops to 0, 0, 1, 1, is not of that kind, right? It goes 0, 0, 1, 1. That's not what a computer would do if it wanted to draw a straight line at 45 degrees. It would go 0, 1, 0, 1, 0. Right, so 1/5 is bad, 1/7 is good. The good rationals are kind of rare. Here's a good one. And in fact, those rationals not only give you extremal points, but those extremal points are corners. There's an angle here. There's an open set of supporting hyperplanes or lines. And the same holds at all of those special rationals. It's a corner, so that means it stays a corner. I mean, it stays extremal if instead of maximizing this linear form, I try to maximize for a slightly different direction. It's still achieved at this corner point. But in fact, I could even modify f outside of linear form functions on R2. I could take some other smooth function on R2, try to compute those averages, and it will still be optimized by this same rational in a small neighborhood. So that was kind of a striking result. And I'd like to say one more thing about these Sturmian words, these special words. They have very low entropy. They have null entropy, which means that if you take at one of those 0-1 words, even for an irrational slope, the set of subwords of length k is only k plus 1. Right? So for example, you have zeros, you have ones, so there are 2 words of length 1, but you cannot have all 4 words of length 2. You cannot have both 0, 0 and 0, 1. Sorry. You cannot have both 0, 0 and 1, 1. You have 0, 1 sometimes, 1, 0 sometimes, but you never have 0, 0, 1, 1. So that's why 1/5 is not there. And in general, you have only k distinct of the 2 to the k possible subwords that could occur. So that's a very low behavior, and for this reason, it's called null entropy, 0 entropy words. So this stability of, this behavior, the fact that it's generically achieved by the extremum is achieved by a periodic orbit, and that this orbit is stable under small perturbations, both of the system, because hyperbolic systems are dynamically stable, and of the map F. This stability was tested experimentally in the 90s by, I think this came from physics, essentially, Hunt and Ott. And so there's a large body of conjectures around this, and some good recent partial results by these people, Contreras, Jenkinson. There's a good survey by Bocci online, if you look for him on the archive. And one thing I could remark here is that if you change F by adding to it a function like this. It's called a co-boundary, but it's a scalar function minus its push forward by t. Or it's pulled back by t. The behavior, these terms will telescope out in the ergodic sum. So the average for f is the same as for f prime. And therefore, a nice question to ask is, can we adjust f by such a g so that f prime, which has the same convex of possible limits, takes its values only in the limits. So it takes the special rationals directly to those points and everything else inside. And this question has, it's kind of subtle. The answer will depend on the regularity of f and will also depend on the dimension. And when you can do it, it's called a Manier lemma. That's an important keyword in the subject. So conjecture, when t is hyperbolic and when the map is generic, then the extremum is carried by some period, some closed orbit that's robust to small perturbations. And in general, even if it's not a closed orbit, it should be a very special kind of orbit. It should be an orbit for which the ergodic measure has zero entropy. Right. So this is the content of what Bush proved in his result above, in the very special case of the angle doubling map, and that's conjectured to be completely general. So my message for today is that these limit cones of Anosov groups, the log spectra, they distribute a lot like the points in the ergodic sum. Right. So unlike with flipping coins or identical sums of IID variables, where looking at the extremal behavior would just tell you something about your original measure that you're taking your variables from. Unlike that, the analogy is dynamical optimization, ergodic optimization. And the points realizing the corners of this shape, they look very much like the Sturmian words with low entropy and so on. So here's an example which was worked out by Thurston in the 80s. So in fact, it's older than the Hunt-Ott phenomenon. The example will be familiar to some people here. You start with a representation that's really two representations, rho prime in the product of these two Lie groups. It's not Zariski dense in SL4, but you can make sense of everything in this context. You have two representations, which is the same as saying you have two hyperbolic metrics on your surface. And what are lambdas? Well, the two coordinates of lambda are essentially the lengths of geodesics in the two surfaces. Right? So any given geodesic has a length in the first and a length in the second surface. That gives you a point here in the quarter plane. And you look how those distribute, and that's really a special case of everything I've been saying before for Lie groups. And Thurston investigated this very limit behavior in a preprint in 1986 called Maximal Stretch Maps. And he showed the following. If you look for the extremal slope here, it's true for a super, also for an inf, the extremal slope representing the largest possible ratio between length in L prime. Sorry, I should have called the long one L prime and the short one L, doesn't matter. The extremal slope here is approached by points, elements gamma that are represented by simple closed curves. So I don't even need to worry about these curves. They will never achieve the extremal ratio. Only the simple curves matter. They approach the extremum. In fact, they achieve the extremum if we allow measured laminations, which is the natural thing to do here to allow limits of curves. And moreover, there will always exist a K Lipschitz map between the two surfaces where K is this extremum. So in fact, this Lipschitz map has to achieve, if the extremum is achieved by this curve, then this map has to stretch by exactly that amount along the curve and do something less extreme in the rest of the surface. So Thurston proved this, and his preprint has really a lot of a lot to unpack. But as a corollary, you get that since geodesic laminations are exponentially approached by simple closed curves, meaning that when you have such a limit of closed curves, the lamination, then you can find closed curves that are exponentially close to it and have linear length. Because of this, you can estimate the distance between the lambdas of those points representing those curves and the extremal wall. Right, it will be exponentially small in the length of the curve. And really, this exponential approach here is a consequence of laminations having only finitely many spikes separating their leaves. So inside a spike, the leaves get exponentially close, and all you have to do is cross. So you take the union of segments of length L that visit all the big gaps between the leaves of the limiting lamination, and everything that remains will be exponentially small. So you can close up. You can use some closing lemma here to cook up a good curve. And Thurston in his preprint even does the Hunt-Ott thing of proving that generically, for most pairs of rho prime, this extremum will be just one curve which has the extremal ratio. In the context of just pairs of hyperbolic metrics, you can prove that. This proof is not easy to read, but conceptually very, very nice. Generically, in fact, the boundary here is achieved by just the powers of one single element. One here and one in the other boundary. So the Hunt-Ott phenomenon is proved, solved in this special case, which is not a case of ergodic sum. We're not summing variables. We're looking at eigenvalues which don't behave exactly additively. They still have this same type of extremal behavior. And I can say a little bit more about entropy, namely that dynamically such a lamination is an interval exchange. Namely, you take your collection of leaves of the lamination, the limit of curves, and they have a first return map that sort of exchanges them like an interval exchange, and those are known to have zero entropy. And that really gives you it is better than zero entropy, namely the number of words of length n doesn't grow just in a sub-exponential way. With n, it grows linearly, not even polynomially, it's linear with a constant depending on the genus. So the low entropy phenomenon is also proved. Okay. The fan of my computer turned on, and so I'm worrying that you can't hear me as well. Is that the case? Hello? You can still hear me?
Yeah. Hello. Yes.
Yeah.
So what you were saying?
I was asking if the fan that turned on in my computer is covering my voice.
No. It is fine. Perfect. Okay, good. Your voice is coming well. No problem.
While I'm looking at the screen, are there questions about these outlines?
Okay, so is there any question? Okay, so probably no question.
I'm now going to focus on the results that we prove. So everything in the rest of the talk is joint results by Jeff Danziger, Fanny Kessel, and myself. I won't mention it in the theorems. I will outline 3 results, really. One is a version of what Thurston does, but for a triple or more, a tuple of representations in PGL2. right? You just don't just compare two surfaces, but three surfaces in a kind of three-way criterion. Second result will be about subgroups of PGLN that are what's called P-min Anosov. P-min is the smallest parabolic subgroup. So P-min Anosov means that all the gaps between all the eigenvalues tend to grow linearly in word length. And we will show that in this case, the distance to the boundary wall also tends to zero. But the best we can get so far is a polynomial convergence. So the distance of the nth element at distance roughly n here is n to the minus a constant. We conjecture that it's in fact always exponential, and we can, third result, prove exponential bounds in some cases. The Hitchin representations, which are a special case of P-min and Anosov, they're cousins for free groups, which are the positive representations, and also something we call S-transverse, which is even weaker. So under some special assumptions, we can prove exponential distance to the supporting hyperplanes of the limit cone. The recording just stopped and restarted. Is that
right?
Okay.
Yeah. So it was we could not listen to you in the last 2 minutes. There was some problem.
The last 2 minutes.
Last 2 minutes, yes.
Okay, sorry. So, but hopefully you could read. I was just outlining the
yeah. You were on
nature of the three results.
minimum Anosov groups. You were on the second point when line was disconnected. Okay.
So for P-min and Anosov, we can prove a slightly less good than exponential. Okay, a less good, only a polynomial convergence to the, or inverse polynomial convergence to the wall. And for Hitchin or weaker positive or even weaker transverse, S-transverse representations, we can actually prove exponential convergence. And also, and it's really part of the proof, show that the limiting elements have zero entropy, that they behave like laminations in the surface. They have, well, they're not I'll show you later what we mean by quasi-lamination and anti-lamination, but there's a sort of lamination-y behavior of the extremalizers. Okay, so first result, the result about multiple copies of a hyperbolic surface. So you take rho 1, rho r, representations of a surface group, all Fuchsian. So that's the same as taking r different hyperbolic metrics on S. And each curve in the surface S gives you r lengths, L1 through Lr in the surfaces. And you can convert this to a vector of lengths in r to the r. So here's the picture we had before for r equal to 2. So Thurston told you something about what happens here and what happens there. And when you crank up r to 3, for example, then you can, well, it becomes harder to draw everything. But you can still projectivize. And if you projectivize this, this orthant, what you see is a triangle, right? So here's the triangle, and here's the projectivization of all the log spectra, and the projectivization of the limit cone, which is this convex subset. So what do we know in that case? Well, one important thing to notice is that unlike when r equals 2, where there were only 2 extremal behaviors to worry about, the top and the bottom, now there's all these potential ways that you could extremalize the tuple, right? There's continuously many possible curves or laminations or extrema to worry about. So here's the theorem that we can prove. If, okay, so we know that P of lambda is a convex body like this, and we also know it doesn't touch any of the walls because the hyperbolic metrics are mutually quasi-isometric. So it is some some convex shape disjoint from the walls of the projectivized Weil chamber. And if you are interested in a supporting plane to it, such that the supporting plane sees on one side of it one of the corners of the chamber, and on the other side it sees all the other corners, plus all the limit cone, and also the center of the Weil chamber. Right, so this H is an example of that. And here, I guess here would be a bad example. This is a no. This is a yes. This is a no because it sees two of the corners on the wrong side. Okay. So there are some bad regions of support here and there that we can't say anything about. But for all the rest, the point, the intersection point between the supporting plane and the limit cone is achieved by a limit of simple flow curves. Not only that, but there is exponential convergence and everything like laminations. So you actually do get laminations, just like in Thurston's result. So you notice that in Thurston's result, the assumption was that you should have the central ray and the vertical axis both on the same side. And in fact, it's if you take representations like this, which cannot happen for closed surfaces, but can happen for surfaces with boundary, and the spectra can distribute like this, and then the behavior is very different. Okay. So just a word on the proof. So how do you prove that you cannot get near here? Sorry.
François?
Yes.
You suggest that there are bad supporting hyperplanes in regions, not points? Is that, is that clear?
What you know is that this is a convex shape. So the regions on which you can have bad hyperplanes, you can detect them. You run a tangent through here and a tangent through there. And the arc between their tangency points, sorry, I'm going to do this for a circle. For a, yeah, let's imagine a circle like this. You run this tangent and you run that tangent. There are tangents here and there. And these are the points that have a bad hyperplane. Sorry, these are the points at which all the hyperplanes are bad. As soon as you have one good hyperplane at your point, you're good. Does that make sense? I can't hear you, but I'm going to assume that this makes sense.
So on the left-hand side of your triangle, it looks like from here, that extreme point is very sort of pointed. And so the supporting hyperplanes would then flip without passing through, well, at each point there would be
this hyperplane is good.
Yep.
This hyperplane is also good at the same point, but for different reasons.
Yep. Yes.
And in between there are some bad hyperplanes, but we don't care. As soon as there's one good hyperplane, the point is good.
So I think Mike's question was, do you always have that like pointed behavior like that one, or do you sometimes have the sort of the rounded one like you said before?
Remember, you really have pointed behavior everywhere,
right?
Or at least that's what you expect. It's really full of corners. So some corners are more pointy than others. They will usually correspond to short curves, and some are pointy enough to reverse behavior, right? So before the point you see this point, this vertex on the bad side, and after the point you see this other vertex. But sometimes there will be a whole bad region at which no supporting hyperplane satisfies the assumption of the theorem. It just really depends on where the pointy points of the convex shape are. If they are close to the if there's a not very pointy part running along a side like this, then you expect you expect to have points that you won't be able to treat with our criterion.
So
Making sense? You can nod. I can see you nod even without the microphone.
Yeah. So the question was whether you know there are regions or whether that's a possibility. I mean, is it?
I think we can cook up such examples, yes. Because we control a lot of things in the case of the punctured torus. And I will say a few words about this later. Not about this specific question, but it should give you a sense that we have enough control. Okay. So a word about the proof. Sorry, just to keep things in focus. We are trying to explain why a point that's very extreme like this cannot be approached by curves that have intersections, that have self-intersection. Or if you have curves with self-intersections that approach it, then you have even better curves, shorter with less self-intersection that also approach it. So how would you go about proving something like this? Well, you resolve crossings, right? When you have the two in the universal cover of your surface, so that's really are copies of the universal cover, one for each representation. Well, your curves cross in each factor. There's always an angle theta, and in terms of this angle, you can estimate the new lengths that you would get by resolving the crossing. So that's some trigonometric formula in terms of theta. You do this for all your representations, and then you use some concavity of the trigonometric functions involved to show that provided the coefficients are of the correct signs, which is really the assumption they made about the position of H, that will improve the linear form applied to that tuple. Right, so it's not very different from what Thurston does. He sort of phrases it differently, but it's also really a resolution argument that he makes. And importantly, the curves, the pair of curves need to cross in every factor. So if you do this with a free group and it represents different surfaces in each of the factors, then maybe there's a pair here that doesn't cross, and here there's a pair that does cross. And then all of your trigonometry breaks down and you can't do this uniformly anymore. Okay, but in this good case, you can actually produce laminations. In the case that breaks down, you can also do stuff, but I'll talk about this later. We can use these estimates to compute the shape exactly in some cases, reproducing all of the features of Busch's theorem with the funny shape. The corners are exactly all of the simple closed curves in the torus. And by contrast, we can also cook up situations for different groups where, in fact, P, the domain, the projectivized lambda, I think I call the shape P, can be also a finite polygon, depending on how you arrange things. So here is a sort of cartoon of what we do. You take this punctured torus, so it's really generated by this translation and that translation along the curves of slope 0 and infinity. Here's a cartoon of its convex core with some colors, so we see what maps to what. For example, this yellow patch maps over to this yellow patch by the blue translation and so on. You name all the slopes, and then you make, starting from this equilateral situation, you make one of the slopes very short, or the other, or the third, and those are your three representations. So for example, in this representation right here, the curve alpha 0, if you can see the color, the red curve here, is shorter than the other two. And so you end up closer to the bottom side. Here it's the blue curve that's shorter than the other two, so you end up closer to that side, and so on. And these turn out to be corners. And you can show that in this case, everything is nice and cornery. Okay. By contrast, you have also situations where, see, what happens here is that the curve 1/2 is the composition of the curve 0 and the curve 1. It's really you are in the torus, or 0 and infinity. You have one curve, another curve, and then you compose them doing horizontal and then vertical, and that's your new curve. So there are situations where the length of the new curve is always close to the sum of the two lengths in each factor, but there are situations where close is on the other side, the wrong side, and then no matter how many times you keep doing the operation, the composition, you will always end up on the wrong side, on the opposite side of the initial segment, and therefore there's nothing in here. It really all depends on what the group is and how you arrange the three representations. But we have a lot of control for this, and I believe we could also arrange for this shape here to be more like this, or more like, to answer Mike Wolf's question, if you can arrange for your triangle to look like this, then there will be whole region down here that look bad from the point of view of our theorem. Okay. So much about PSL2 to the R. Now I'd like to talk about representations in the full linear group PGL R+1. I use R+1 because that way the rank is R. There are P-min and Anosov, meaning that every element is split with distinct eigenvalues, and the gaps between those eigenvalues grow. The fact that they grow means that this shape here, the projectivized limit cone, does not touch the boundaries of the Weilsheim. So the two eigenvalues never coincide. And the question is, how can we find, or maybe I should say construct, and I think my favorite word is breed, good elements gamma that end up close to the boundary. Here's the general philosophy. For Anosov representations, in fact, the group gamma has to be hyperbolic, word hyperbolic, and therefore you can think of geodesics on the group as the geodesic flow on a certain negatively curved compact manifold. Really, you have to use something called a flow space, but in our context for a surface group, you could just use the hyperbolic surface. Gromov and Champetier-Minayev and Minayev gave a version of this for a general hyperbolic group. There is a thing on which you have both. It's a space, a metric space, with an isometric action by gamma, a flow by R, and good compatibility properties. You can really think of it as the unit tangent bundle of your surface, or universal cover. And not only does this object exist, but the Anosov condition says that there are good Hölder maps from this object, this flow space, to the symmetric space of our Lie group PGL R+1, which would be what generalizes the hyperbolic plane, taking each flow line into a flat. So instead of taking the flow lines to geodesics, you have flats. Here's the cartoon of a flat when the rank, well, in PSL3. PSL3 flat, and each flow line gets taken into its flat, and a nearby flow line will be taken to a nearby flat. And when you do the surgery operation on two flow lines, well, surgery operations are well defined. The flow space has a closing lemma, meaning that if you take a flow line and then another flow line passing near its endpoint, and then near its stop. You stop somewhere, and you jump to a nearby flow line. You stop somewhere, you jump to another nearby flow line. You can keep doing this for as long as you wish. There will always be another flow line overall, a single flow line that fellow travels everything very close. This is true in the flow space. It's true in the hyperbolic plane. It is not true in the symmetric space, but the only reason it's not true is that maybe the two geodesics are both in the same flat, and that's not supposed to happen. In fact, for Anosov representations, it does not happen. Two distinct flow lines go to distinct flats. So you can sort of do these surgeries, and in fact, you just have to learn to do this, what I call the, sorry, what was this? This slack computation. You just have to learn how to do it instead of doing between geodesics of H2, you have to do it between four flats of the symmetric space. So it's some other matrix computation, some other more advanced trigonometry, but you can give formulas that say by how much of the length will be updated when you do these surgeries in the flow space. So upshot, because the flow space mod gamma is compact, when you have a long closed orbit L gamma, representing an element gamma in the flow space, it must have closed self-passes just by compactness. It passes close to itself. And then you can ask yourself, okay, what kind of surgery could I do? I mean, there is an obvious surgery to do here. Could make a shorter element here and a shorter element there. And so if gamma was best so far, it was the element that brought you closest to the supporting wall of the limit cone so far, then it cannot beat out gamma 0 by very much, because that would mean it loses out by gamma to gamma 1, since the surgery is at a really close self-pass. You have almost exact additivity between the three lengths. So if one of these was more efficient at being close to H, then the other would be less. So the improvements, as you take better and better elements, gamma I, longer and longer elements, each best so far, it can never beat the record by very much. The increments are extremely slow, and you can turn this whole concept into a theorem that says the distance to the supporting hyperplane is really a negative power of the length of gamma. And because, I mean, you should be able to see this from the way I told the story. This scale, I mean, this order estimate, the size is really just a function of how close the self-pass is, because that quantifies how exact the quasi-additivity is under surgery. And so this minus d comes from the fact that there's a Hausdorff dimension of the flow space. So just by the pigeonhole principle, you have to come n to the minus 1 over d close to your starting point after travel of length n. So that's a very crude estimate of how close the self-passes are. But in the case of laminations, the self-passes are exponentially near, right? Just because of this pinching, this spike behavior in a hyperbolic surface. So to improve our estimate here, we really have to get better guesses at what types of elements can be so extremal. They probably don't go everywhere, which would leave us only with the pigeonhole principle to estimate the closed passes. They probably don't go everywhere because they have to stay very optimal all the time, just to be the optimum curve. So this is very crude. In fact, for lamination, you have much closer self-passes than for generic curves. And we're going to try and exploit this in the third result. So here is a few minutes left. Third result about Hitchin representations. What's a Hitchin representation? I won't have time to really define what they are, but people have been talking about them this week. It's a type of representation of a surface group into PGL R+1 that generalizes all the good properties of Fuchsian representations. Especially, not just those, but especially the positivity properties, which means it's a representation that somehow does justice to the fact that there's a cyclic order on the on the space at infinity of the group, on the limit set of the group. So what is positive? I printed it very small here. It's really certain matrix coefficients in the matrix expressing the relative positions of certain flags. So the point is something is positive. Now, in this situation, for Hitchin representations, if you're given a closed orbit, L gamma in the flow space and a closed self-path, you can predict by positivity the dominant order of the direction of the update, right? Your new curve gamma is a combination of two old curves. That's why I call it breeding, right? You have two short curves and your new champion is just the product of the two. And the update in terms of length, the lambda of gamma compared to the sum of the lambdas that you had previously can be as a vector of R to the R. You can predict it to dominant order very precisely. In fact, it's almost exactly along what's called the root of the smallest eigenvalue gap. So as a consequence, depending on how H lies and how the vertices lie and how everything lies, you can predict on what side of H this update is going to put you. You can predict if your offspring gamma is better or worse than its breeders. It will depend on H, on the coefficients of the linear form that I'm testing. But if the coefficient in front of of this dominant term that we could estimate is positive, then we're good. So what the form of the result that we prove is that depending on the relative positions of H and of the corners and on which sector of the Weil chamber we are in, the gamma n that approaches X, that best approaches X, must have all its closed self-passes correspond to crossings, or maybe all correspond to non-crossings in the surface. So non-crossings means it ends up looking like a lamination. And if all the self-passes look like crossings, it looks like what we call an anti-lamination. And I should insist that it's only true for close enough self-passes. So that means close enough that we can trust our estimate of the dominant order of the update. So here's a picture of a lamination in the hyperbolic plane. Here's a picture of what we call a quasi-lamination. It's like a lamination, except things are allowed to cross so long as they are transverse enough. So there are no small angle crosses between curves. So for example, if you have a lamination in a cover of your surface that projects down to a quasi-lamination of the surface. But there are more general quasi-laminations than that. And here's an anti-lamination where everything has to cross. And all of these things have the exponential self-return properties, which allow us to prove exponential convergence to the wall in the same way as for laminations in the Thurston PSL2 to the square situation. Okay, and the last thing I wanted to say is that this conclusion of exponentially fast approach still holds if you don't have positivity of the positive representation, but if those matrix coefficients that are supposed to be positive, if they are just known to be non-zero, right? They form a certain compact subset of R. And if you know this subset doesn't contain zero, which is stable and there are small perturbations of the representation, then the whole thing goes through. Just have to modify laminations and anti-laminations to some intermediate adapted notion. So you can in fact capture some extra examples like this, for example, by ping pong. You take generic flags, strong ping pong projective transformations between them. If the flags are generic enough and the eigenvalue is strong enough, that will satisfy the assumptions and you have the exponential estimates. Okay, I'll stop here.
Any question?
My question is, in the quasi-lamination case, do you have any control about what, I mean, how many intersection points you have, or if they are dense, or if they're discrete or something? I mean, do you have any control in the definition about those points?
So, okay, I should really call this epsilon quasi-lamination, meaning that every intersection between leaves should have angle at least epsilon. Okay. And one estimate you can make is, depending on this epsilon, there is an n, such that you can carry your quasi-lamination on a sort of train track with n branches. The branches are allowed to cross, but the n is uniform. That probably gives you the right concept. Does that answer your question? And there's also a train track carrying these things, by the way. You just have to imagine that it's an amusement park train track where the trains are allowed to fit.
My second question, is there a preprint?
Okay. For result number 1, there's a paper that's essentially ready that we'll put out soon. For 2 and 3, it's still only a draft. So we won't be able to show it for a few months.
Okay, thanks.
So, any more questions? John, you have a question?
I'm sorry. I should quote Nolte here, who proved something close to this. He has some other examples where he makes polygons. Nolte.
Okay. So, okay, thank you, François, for this interesting and very colorful talk. So I really like your slides, full of colors and nicely organized.
Thank you very much.
Yeah. So thank you very much. Thank you for being with us online. Thank you.
Enjoy the rest of the conference.